Hello everyone, welcome to this lecture on convolutional neural networks. Today, we are going to learn about a very important concept in convolutional neural network which is called as filters and why we really care about them. In the previous lecture on convolutional neural network, we have looked at why normal neural networks are not very good for classifying images. So, for example, the goal of convolutional neural networks is to look at this image, for example, and conclude that it is an image of a cat. The question is, why don't we use normal feed forward neural networks for this task? It turns out that normal neural networks don't exploit or don't use two very key features of using images as data. The first key feature is spatial locality. This means that all the features or the pixels which correspond to a cat will be close together. For example, the pixel which corresponds to this eye will be close to the pixels which corresponds to this eye. The pixel which corresponds to this ear will be close to the pixels which correspond to this ear. Traditional neural networks don't take advantage of this feature or this property of images, the property of spatial locality. The second feature of images as data is that of translational invariance, which means that in this image, whether the cat is slightly shifted to the right, left, top, or bottom, it will remain a cat. Uh, these features of images look simple, spatial locality and translational invariance, but they are hugely beneficial, and we need some architecture which takes advantage of these features. Traditional neural network with neurons and layers don't take advantage of these features at all, and that's why they were not very useful in tasks such as classification of this image. And that's the reason people turned to convolutional neural networks. One of the key concepts in convolutional neural networks is that of filters. In fact, the whole of CNNs or convolutional neural networks will be much easier to understand if we understand what are filters. Filters are the true building blocks of convolutional neural networks. And if you have used tools like Instagram or Snapchat before, you might be knowing of filters. Or if you have used your phone camera and if you have changed the filter to bright or dark or to some any other filter, that's exactly the kind of filters which we are talking about here. But we'll talk about them in a bit more mathematical sense. We will also introduce the term convolution and why are these neural networks called convolutional neural networks. I'll try to explain everything from scratch so that you will understand from the very basics. Today we are going to learn about filters on one dimensional images and the convolution operation on one dimensional images. We have another lecture after this in which we'll start looking at two dimensional images such as the cat over here and the convolution operation on the two dimension image. Let's get started with today's lecture. We will first start with a one dimensional image which looks something like this. So here you can see the image starts with a dark color here, then it transitions to a lighter color which is white, then it becomes dark, then it becomes light, and then it becomes dark again. This is the one dimensional image which we have. In pixel representation, this looks something like this. All the dark spots will be represented by zeros, and all the white spots will be represented by ones. So the pixel representation is 0 0 for the black region here, 1 1 1 for the white region here, then 0 for the black region, 1 for the white region, and then 0 0 0 towards the end for the black region at the end. That's the input data which we have. This is a one dimensional image. Remember, when we look at an image, we will see it as a series of dark and white bands, right? But when computer looks at this image, it just sees a bunch of pixels. So this is the data which is available to us. So I'm just writing it over here as data. Now the goal here is that we want to detect left edges in this image. What do I mean by left edges? Left edges means that whenever there is a transition from black to white. So let's see where all there are left edges. Here there is a left edge, right? Because there is a transition from black to white here. And here there is a left edge because there is a transition from black to white. I want to detect left edges just from this pixel representation here. So somehow the answer should be that there is a left edge over here and there is a left edge over here. Remember that we can see the left edges clearly, but that's not the main goal. The main goal is for us to help the computer understand where the left edges are based on this pixel representation. And to achieve this goal, we need to look at transitions from 0 to 1 pixels, because as I mentioned to you, we are looking to capture the black to white transition, right? In pixel, that means we are looking to capture transitions from 0 to 1. That's the goal represented in terms of mathematics. How can we do this? This is where filters actually come into the picture. It turns out that filters are a great way to detect features like these, such as left edges in the image. So, to achieve this goal, we are going to start with a filter which is called as the left edge detection filter. Okay, and I'm going to intuitively assume this filter. Not all filters are this intuitive to assume. So since we are looking at a left edge detector, we think that there has to be a transition from something low to something high, right? So I am going to use this filter which has essentially two values. It has the first value as -1 and it has the second value as +1, and I'm going to call this as a left edge filter. For a right edge filter, I would have used +1 and -1, but I want to detect transitions from a darker region to a lighter region. So I'm going to be using this filter which has two values, -1 and +1. And then what I will be doing is that then I will be doing something which is called as the convolution operation. What this convolution operation means is that I'll take this filter, I'll take this image representation, and then I'll run this filter across the image and take dot products at every single time. If you are not familiar with dot product, let me first introduce that concept to you. If there is one vector, if there is one vector v1 which has essentially two values a1 and b1, and if there is a vector v2 which has two values a2 and b2, then the dot product of v1 and v2, which is also represented as v1 dot v2, is the product of the first terms a1 a2 plus the product of the second terms, which is b1 b2. So that's exactly what we'll be doing here. We'll be taking this left edge filter, which you can think of as a vector with two values -1 and +1. We'll be first starting from the left hand side. So we'll put this left edge filter over here, take the dot product with the first two entries, and then keep on sliding the left edge filter across the image. Let me show you how this looks like in practice. So this is my image, right? This is the pixel representation 0 0 1 1 1 0 1 0 0 0. So this is my filter. So as I told you, the first step in convolution is to take the filter and align it to the left side of the image. So first I'm going to take this filter and align it to the left side of the image. Then I'm going to start taking dot products. So initially I'm going to look at these two values over here. And then I'm going to take a dot product between this vector 0 0 and -1 and +1. And remember, in dot product, the way we do the dot product is we multiply the first entries and then add the multiplication of second entries. So it will be 0 into -1 plus 0 into +1. So the resulting answer will be 0 over here. Then what we do is that we'll take this filter and slide it to the right. Then we will be taking the dot product between the second value and the third value, which are these two. So then we'll take the dot product of 0 and 1 with -1 and +1. So the answer of that will be +1. Then I will slide it further. I'll slide the filter further to the right, and then I'll take the dot product of the filter with these two. Then so that results to an answer of 0. Then I'll slide the filter further to the right, and then I'll take the dot product of the filter with these two. So that means that I'm taking the dot product of 1 1, which is the first vector 1 1, and the second vector, which is minus 1 and plus 1. So then we'll multiply these two terms, which will give me minus 1, and add the multiplication of these two terms, which is plus 1. So that's why the result is 0, as you can see here. Then I will slide the filter further to the right, and then I'll take these two terms, and I'll take the dot product with my filter vector. That will give me a result of minus 1. Then I'll slide further to the right, take the dot product with 0 and 1. That will give me a result of 1. Then I'll slide further to the right, take the dot product of 1 and 0 with minus 1 and plus 1. That will give me a result of minus 1. And then finally, I slide once more, take the dot product of 0 0 with minus 1 and plus 1. That will give me an answer of 0 over here. Then I will slide one last time to the right, which is 0 and 0, and that will give me a dot product of 0, which is over here. So let me collect the values which I have seen so far. So first, let me write the input data here. So the input data was 0 0 1 1 1 0 1 0 0 and 0. Correct. So then we started taking dot products, and the first dot product, let me change the ink color so that the reading becomes easy. Okay, so the first dot product which we took was here, so the answer was 0. Then with the second dot product was which we took here, so the answer was 1. Then the third dot product answer was 0, which was here. The fourth dot product was 0. The fifth one was minus 1. Sixth one was 1. Then here we had minus 1, and then we took here 0, and then we took here 0. Okay. So first thing which I want you to notice is that look at the answers over here and try to see where the answer is plus 1. So you'll see that the answer is plus 1 exactly at two locations, this location which I've marked in circle and this location which I've marked in circle. So here I have marked these with the orange circle here. So these locations where the answer is plus 1 are my left edges. So these are exactly the locations where there is a pixel transition from 0 to 1. See, here the convolution operation is plus 1 because here the pixel transitions from 0 to 1. Here also the convolution operation result is plus 1 because the pixel values transition from 0 to 1. So if you trace these pixel back, we have the second pixel and we have the sixth pixel. So let's look here. From the convolution operation, we have predicted that the second pixel here and the sixth pixel, which is over here, are the edges, are the left edges, which is exactly what we wanted, or which is exactly what we had predicted in a visual manner. So the convolution operation has actually allowed us to identify left edges in the one dimensional image which I just showed to you. One thing which I want you to notice is that look at the number of entries in the result. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9 entries in the result, right? 9. But look at the number of entries in the image data: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's going to be a problem for us. We want the result dimensions to be same as the data dimensions. The reason this is happening is that every time you do a convolution, you take the current element and the next element, right? So when you move to the second last element, you take the second last element and the last element and then do the convolution with minus 1 and plus 1. But when you move to the last element, there is nothing after the last element. So that's why it's difficult to do the convolution operation. So what we do here is we introduce something called as the padding, which means that if there is nothing after the last element, we introduce a hypothetical or a not real value of 0 over here, just for the sake of computation and just for the sake of making sure that the sizes of the output are consistent with the sizes of the input data. So then what will happen is that since it is 0 anyways, it will not contribute to anything, but at least we'll be able to take the dot product of this vector 0 0 with minus 1 and 1. So then this will also lead to an answer of 0. So finally then the output vector will have 10 data points, which is very similar to the number of data points in the input data. So this is called as padding. So when we come to even two-dimensional data set, and when we do the convolutional operation with the filter, to match the size of the output with the input, we need to pad the input data with zeros so that the sizes match. So if you think of the convolution operation, it's actually pretty simple. We just take a filter and we run it across the image. So this is the filter for now, minus 1 and plus 1, and we run it across the image. You start from the left and then you sequentially keep on going towards the right, and every time you move to the right you take the dot product between two elements here and the elements of the filter. As you reach the end you will see that there is nothing after here, so you pad it with 0, which is a fictitious or a not real data, just to make sure that the sizes of the output and the sizes of the input are consistent. So the first thing which you learn from this exercise is that filters help us to detect features. Filters help us to detect features in images. It's very important for you to keep this in mind. This is why you will appreciate why we learn about filters in the first place. When it comes to images, filters really help us to detect features in images, and it's not easy to come up with these filters. Right now I just magically came up with this filter, right, minus 1 and plus 1, because I had the intuition that we had to detect the left edge. But to detect more complex features, such as maybe the whiskers of this cat, or the ear flappiness in this cat, or the edges here between the cat and the background, to detect some of these features, or the stripes in the cat, it's not easy to come up with simple filters. So humans cannot come up with these filters every time. That's why we need neural networks. Okay, so currently I have detected the left edge with this filter minus 1 and plus 1. If I were to detect the right edge, then I will use the filter plus 1 and minus 1. And I have a quiz question at the end of this lecture, which is, if you have an isolated pixel. So for example, if this is the image data, and if you want to detect this isolated pixel, this is an isolated pixel because it's surrounded on all sides by the black region, right? So this is an isolated pixel. If you want to detect this, what is the filter which you will use? To detect the left edge, as we saw, to detect this left edge, for example, we will use minus 1 and 1. That's fine. To detect the right edge, which is the transition from white to black, we will use the filter plus 1 and minus 1. But what about this isolated pixel over here? What filter will you use to identify this feature which lies between two black regions, which is a white region which lies between two black regions? Remember, to go from dark to light you use the filter minus 1 and plus 1. To go from light to dark you use the filter plus 1 and minus 1. Now you want to go to dark to light to dark, so what filter will you use? Please pause here if you want to think about this, because I'm going to reveal the answer now. Since we are since we are going from dark to light to dark, the filter which turns out to be the best in this case is minus 1, plus 1 and minus 1. So if you have a data set like this, let's say, of one dimensional data which has a huge number of pixels, and somewhere in the middle you have an isolated pixel. So somewhere in the middle you have an isolated pixel uh, like this, and everywhere else, let's say, it's white. What will happen is that, so the pixel value here is 1. Let me write it with a different color. The pixel value here is 1, 1 and 1, and here it is, I think, 0, 1 and 0, right? Okay, so now let's see what will happen when you convolve this filter, which is minus 1, plus 1 and minus 1, this filter over here. Let's see what happens when you do the convolution operation between this filter and this image. First we'll start with this pixel. So we'll align this this filter on the left hand side. So we'll take the dot product between 1, 1, 1 and minus 1, plus 1 and minus 1. So that will result into a value of minus 1. Then I will move here. So then the vector will be 1, 1 and 0, and I'll take the dot product between minus 1, plus 1 and minus 1. That will lead to an answer of 0. Similarly, here you will get some answer, but you will find that this particular pixel is the only place where the answer is plus 1, because if you take the dot product between 0, 1, 0 and minus 1, plus 1 and minus 1, the answer will be plus 1. Everywhere else the answer will either be 0, or the answer will be minus 1, or the answer will be minus 2. This pixel right here is the only place where the answer will be plus 1, and so that will help us to detect that this is the only place which is an isolated pixel. So this is how convolution operation and selecting the right filter can help us detect features. So not just left edge, right edge, but right now I showed you how to detect an isolated pixel as well. I highly encourage you to just open a notebook, write this vector, and do the convolution operation with this isolated pixel filter, and slide the filter from left to right. You will see yourself that this pixel is the only place where the answer is plus 1, which gives us an indication that that's the only isolated pixel in the image which we are considering. Okay, so the first thing which you learned here is that filters help us to detect features in images. And the second thing which you have learned here is that padding. So to make sure that the output size is the same size as the image input, we need to do padding on the data set or add pixels of zeros. That's the second thing which you learned. And the third thing which you learned is the convolution operation. So convolution operation is very simple if you understand dot product. So if you have two vectors, 1 1 and minus 1 and plus 1, the dot product is just 1 into minus 1 plus 1 into 1. If you have three vectors, let's say if you have vector with three values, a1 b1 c1, and another vector a2 b2 c2, so let's say this is v1 and let's say this is v2, the dot product of v1 and v2 will be a1 a2 plus b1 b2 plus c1 c2. So remember, when you are taking dot product, first you multiply the first term, then you add the multiplication of the second term, and then you add the multiplication of the third term. If you remember this, the convolution operation is very easy to understand. You just have to slide the filter from left to right and take the dot product at every single stage. Okay, so that's it for this lecture where we learnt about one-dimensional filters and how one-dimensional filters can be used to detect features in images such as the left edge, right edge, and isolated pixel. In the next lecture, we are going to be looking at two-dimensional images, and we are going to be looking at the filtering operation in two dimensions. And then we'll also take a fun example about how we can detect features in two dimensions. Thank you so much, everyone, and I look forward to seeing you in the next lecture.